The section today is infinite geometric series. So just to remind you, an arithmetic series is one where you're adding a number like this, d equals 4. You're adding a number to get to the next term. A geometric series, geometric sequence, I should say, is one where you're multiplying by the same number. So this is r equals 2. So today we're talking about a geometric series. A series is when you're adding a bunch of terms. So you should know that vocabulary, the difference between a series and a sequence. And you can find the definitions in your class notes. But today we're talking about an infinite geometric series. So geometric series, we've talked about those on previous lesson, but now it's infinite geometric series. So we're going to add an infinite number of terms. So infinite geometric series, no last term. N is approaching infinity. For an infinite series, the sum S of n is called a partial sum. Since you can't add the last term, since you don't know what the last term is, it is all the way to infinity. But the formula is this, the sum of an infinite geometric series, the sum S, notice it's just an S, there's no n because n is infinity. So, the sum S of an infinite geometric series, when r is between -1 and 1, is given by this formula. It's the shortest formula that we have, so it's really easy to memorize, but it's only valid when r is between -1 and 1. That's because, let's take an r value of 0.5 for instance. If you multiply by 0.5, which is between -1 and 1, and you keep multiplying a bunch of times all the way until infinity, I'm not going to go infinitely, that would take too long. But notice the number keeps getting smaller and smaller and smaller and smaller. I don't know how many times I hit that. But it keeps getting smaller and smaller and smaller. That will happen for any number between -1 and 1. It's basically exponential decay, which we talked about in chapter 10. Exponential decay. Okay, it stopped. It doesn't work for a number like 3. If you keep multiplying by 3, it's not going to get smaller and smaller and smaller. It's going to keep getting bigger, and it gets bigger. And it keeps getting bigger, and it keeps getting bigger, and it keeps getting bigger, and bigger, and bigger, 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 bigger. Okay, it stopped. What's that? 1 trillion. Close to the national debt of the United States. But so it only works, it's only valid, this formula for infinite, it's only valid when r is between -1 and 1. So you have to be careful to see what your r value is. If r is too big, then the series is said to diverge, or you could say it has no sum, or you could say no solution. If you don't like words, you can do that mathematical symbol. So let me show you where the formula comes from. On 11.4, the previous lesson, we solved this formula, which we could write if we distribute the a sub 1. We could write as a sub 1 minus a sub 1 r to the n divided by 1 minus r. And then we could write that as two different fractions with common denominators, 1 minus r, 1 minus r. A sub 1, r to the n. And what I just showed you with that 0.5 times 0.5 times 0.5, that kept getting smaller and smaller and smaller. The r to the n will approach 0. So if you had like 0.5 to the very big number, then that is approximately 0. For all intents and purposes, we'll say it's 0. It's incredibly small. So if that's true, if r is between -1 and 1, n is a very large number, then all of this quantity would be 0. We'd have a sub 1 over 1 minus r minus a sub 1 times 0 over 1 minus r. And this whole quantity is now 0, so we have the sum of an infinite series is a sub 1 divided by 1 minus r, given that r is between -1 and 1. So that's where the formula comes from. To show you some examples of how to use that formula, it's a pretty easy formula. You have sum, infinite sum. A sub 1 is 4 here. Notice your r is between -1 and 1. 1 minus 5/7. And when you put that into your calculator, you would get 14. And you can see that by doing 4 over 2/7, which is 28 halves, which is 14. You can also do one when you're given a sum. This is infinite. Notice there's dot, dot, dot. And you're not told what does n equal. Find when n equals 10. You're not told a number of terms. So you would say the sum, infinite sum. The r value, 16 times something gave you 12. So your r value would be 12/16, which is 3/4. So you would have 16 divided by 1 minus 3/4. And when you put that into the calculator, you would get 64. So why don't you try the next two? The first one you're given a sub 1 and r, and the next one you're given a series. So the first answer is 7.5. For this one, you find that r is negative 1.5. Notice you could still plug the numbers in, but this is incorrect because your r value has to be between, negative 1 and 1, so it's not in between negative 1 and 1. Little slash marks through the less than signs. So you would say that this has no sum. It's not valid to use this formula. When you use the formula, it looks like, you can get an answer for the formula. You could plug that in and get a number answer, but it would be wrong because your r value wasn't the correct condition. So you'd say no sum, or you'd just do no solution for that one. On the next page, we have some sigma notation. Sigma notation, this is infinite sigma notation. Notice the infinity sign at the top of the sigma. These are actually really common in pre-calculus and calculus. You do a lot with adding sigma notation to infinity. And you can also tell it's geometric because of the exponent. It's in the correct form. AB raised to the x is geometric form. AB to the x is geometric form. So the first term is 48, this value 48, and the r is 2/3. And once you get that, it's pretty simple to plug the numbers into the formula. So the sum of the infinite number of terms, 48 divided by 1 minus 2/3. And when you type that into your calculator, you would get 144 is the sum. And then the next one, a sub 1 would be 3, r would be a half. So the sum of the infinite number of terms would be 3 divided by 1 minus a half, which is 3 divided by a half. So the sum is 6. And why don't you try the next two, number 24 and then the one after that. They're both infinite geometric series with sigma notation. So the first one, you get an answer of 1. The second one, be careful, you get an answer of no sum because your r value is greater than 1. And it's not valid to use infinite geometric series. The next question, because of air resistance, the length of each swing of a certain pendulum is 95% of the length of the previous swing. If the first swing has length of 40 centimeters, find the total length the pendulum will swing before coming to rest. So a pendulum, it's kind of hard to draw a picture, but a pendulum will start here, and then it goes back and forth. It's kind of hard to draw, but imagine this line going back and forth. Maybe I can go like this. So the first swing length is 40. Whoops. First swing length is 40. So you have a sub 1 equals 40. R is a percentage you're losing, or you have 95% each time. And notice that we don't know the n. We don't know when it's going to stop. When it stops. So we will use an infinite sum since we want to know the total length that the pendulum swings, back and forth plus back and forth plus back and forth. So you have 40 divided by 1 minus 0.95. And that gives you 800 centimeters for a total back and forth swing. The last two examples, there are 3 different ways that you can answer this question. One way is related to the formula we've been doing in this lesson. I'm not going to show you that way because I think it's too complicated. The second way, I'll show you this way. I think it's really neat. The third way is once you know the pattern, then you don't even have to do the second way once you know the pattern. So write each repeating decimal as a fraction. Let's say we have some number, which is 0.7 repeating. And if we multiply both sides by 10, that would move the decimal place to have 7.7 repeating. And if we subtract these, it'll get rid of the repeating decimal part. So we have n minus 10n is negative 9n. And 0.7 minus 7.7 repeating. The 0.7 repeatings subtract out, and we have negative 7. So the answer would be 7/9. 7/9 is the same as 0.7 repeating. And this idea you can use for bigger numbers repeating, like 0.36 repeating. You have 2 repeating decimal places. So we're not going to multiply by 10. That would be a bad idea. If you multiply by 10, you would get this number, which isn't going to be able to subtract out with a repeating decimal place.
Next is 100.
So you multiply by 100. So if this is your number, 0.36 repeating, you multiply by 100, and then you get 36.36 repeating. When you subtract, you get negative 99n equals negative 36. So n is 36 over 99, which you can divide by 9, and you get 4/11. But the main thing is to notice the relationship, 36 over 99. If you notice the pattern, when you have one decimal that repeats, 7 that keeps going 7, 7, 7, 1, 7 keeps repeating, you have 7 over 9. When you have 2 numbers that repeat, 3, 6, 3, 6, 2 numbers, you have 3, 6 over 2 9s for 2 that repeat. So if I had this, and I wanted to write that as a fraction without doing all this work, you would say 1, 2, 3 divided by how many 9s? It would be 3 9s because you have 3 numbers that repeat. And then you would simplify this, but that's the basic idea. And once you know that shortcut, you don't have to do all the work. I think the work is neat, but that would be the answer. Thank you for watching this video.